Okay, and on to mixed series and parallel circuits. All right, this I think you'll get this no problem. So just make sure you follow along. So let's look at the equivalent resistance of a mixed situation. So what we're looking for is resistors that are only in series or only in parallel, and we're going to break them down. So so can I say that the 2 and the 4 are in series? I can't because they junction off right here. Okay. Can I say that the 4 and the 6 are parallel? Okay, I can because these are strictly in parallel. There's nothing in the way of them being parallel. So what we're going to do is we're going to use the parallel rule. Okay, 6 over 4, 1 over 4 plus 1 over 6 equals 1 over REQ. Okay, and we're going to simplify this circuit down to two circuits, or two resistors. Okay, 2.4 ohms is my equivalent resistance to the 4 and 6 in parallel. Okay, and now these two are just in series, so now all you have to do is add them together, and now I've got the equivalent resistance of that circuit. Okay, that's how the game is played. This is like a little puzzle. It's not too bad. I think the rest of this is sort of like a little puzzle. If you like Sudoku or something like that, you'll probably like this. They're just logic games, really. So what's the equivalent resistance of this circuit? Now, right at first blush, this might look a little out of control, but it's not really that bad. So what we're going to do is look for any circuits that are strictly in series or strictly in parallel. Okay. So these three circuits, or these three resistors, okay, are just in series. So I can collapse them into one. How many ohms will it be? It'll be 12. Okay. So I'm going to take this is that resistor, that circuit. Okay. So here I'm going to take these 4, I'm going to collapse them into a 12 ohm resistor. Okay. Now I want to play the game again. Look for straight series or straight parallel. Okay. Well, right here I've got 2 resistors that are straight parallel. Okay. So I can use the 1 over REQ. Hey, Jordan! Shh! That would be the teenager yammering. So I can collapse these using the parallel circuit rule and get a 3 ohm resistor. Okay. And then I've got now I've got this circuit here where I've got 3 resistors in series. Okay. And then I've got an equivalent resistance of 11 ohms. So the equivalent resistance of all of these is just an 11 ohm resistor. Okay? So that's how the game is played. A couple rules that we're going to be using, and these aren't too bad. So the first one's super easy. The junction rule is that the current, not voltage, current that flows into a junction is equal to the current flowing out. Okay? And the loop rule is that the sum of the voltage changes, okay, around a closed loop must add up to 0. Okay, so let me show you what I mean. So here we've got a circuit like one we looked at before. So what we're going to do is we're going to zoom in on a junction. Now you're going to have to name these currents. Anytime that the wire branches off, the current changes. Okay, so if we call this I1, okay, and that one, we're going to say the current's going out. By the way, if you don't know the direction of the current, it's fine. Okay, just pick a direction, and if you're wrong, it'll end up being negative, and you'll know, oh, it's actually the opposite way, but no big deal. Okay, here we're saying that I3 is flowing into the current, flowing into the junction. Okay, I3 down here. Okay, and this is I1, and this is I2. Flowing out, and the junction rule just says that I1 plus I2 equals I3. The current going in equals the current going out. So I don't think that one's a big deal. Okay, and that works out over here too. I1 plus I2 equals I3. Okay, where I1 and I2 are flowing in, and I1 is flowing out. Like I said, if you're not sure the direction of the flow, just pick a direction, and you'll end up negative if you're wrong, and no big deal. Okay, step 2. Or rule 2. This one is, there's a little bit more meat to this one, but it's still not too bad, I don't think. Basically, if you go around in a loop, you're going to end up at the same altitude. Okay, is basically what this rule says. Okay, if I'm in a roller coaster and I go up and then I go down, okay, and I go around, if I start and end, I'm going to end up at the same altitude. Okay, the same height. For a circuit, we're going to say that you start and end at the same voltage, the same electrical potential. Okay, so and so basically, when you take a trip, okay, the sum of everything is going to add up to be 0. So so let's start my trip. I'm going to come through this resistor. I'm going to lose 1 volt here. We've looked at the circuit before, so we know these are correct. Okay, and I'm going to lose a ½ a volt here. Okay, and then when I come back at the battery is going to pump me up 1½ volts. Okay, and that equals 0. So minus 1.5 plus 1.5 equals 0. So minus 1 minus 0.5 plus 1.5 equals 0. As long as I follow a loop. Okay. Showing you this on a graph. Okay. So my voltage is the same. I drop 1 volt. Okay. My voltage stays the same in the wire, drops, et cetera, et cetera. Okay. So again, showing you on this is similar to the roller coaster analogy. Okay. No matter what, my voltage has to end up at the same height. Okay. Now, when you're using this loop rule, okay, when you follow the electron flow, okay, you go across a resistor, you lose voltage. Okay, that makes sense. So I'm going to end up with negative. So if my current's 2 amps and my resistance is 3 ohms, my voltage drop is equal to minus 6 volts. Okay. If on your travels you go the opposite way on a resistor, okay, if you're going upstream on the resistor, it's plus 6. Okay, so I don't think a big deal there. Okay. Now, if you flow from the negative to the positive side of the battery, if you're flowing basically with the current on the battery, you gain voltage. Okay, so plus 9 volts. Okay. If you go the opposite way in the battery, you lose 9 volts. Okay, if you follow the current with the battery, you go up. Okay, if you go against the stream on a battery, you lose voltage. Okay, so something to remember. So what I want to do is solve this problem using Kirchhoff's loop rule. Okay, so what we're going to do is we're going to start my loop. Okay, and we're going to call this current, whatever current's flowing through this wire, I1. Why not? It's kind of a nice name. Kind of got a nice ring to it. Okay. And we're going to say the current is flowing around like so. Okay. If I guess the wrong way, I probably end up with a negative number, and so be it. Okay. So what we're going to do is we're going to go downstream with the resistor. Okay. So I'm going to lose 8I1. Okay, here. And then I'm going to go downstream because V equals IR. V equals IR. So we're following the voltages by saying current times resistance. Okay. So 8I1 is my voltage drop across here, okay, which is going to be negative. And then I'm going to come across here and I'm going to lose 4I1. Okay. And I'm going to write my equation starting here. I'm going to follow this along and I'm going to go minus 8I1 minus 4I1. Okay. Then I come across my battery. Now I'm following current with the battery, so I go up voltage. It's pumping up the voltage. Okay. And that's plus 5.1 equals 0. So and then you've got one variable and a bunch of numbers. Solve it and you're done. Okay. Now this is not mixed series parallel. Mixed series parallel makes it a little bit more interesting. A little bit more of a challenge, but not non-doable by any means. Okay, so if we look at one that's mixed series and parallel, what I wanted to show you here was these are the voltage drops across each one of these resistors. Okay, I've calculated these ahead of time. So 60 volts, 20 volts, 20 volts, 20 volts, 60 volts, and 80 volts. Okay, what I want you to see is no matter what path you take, okay, 60 plus 60 is 120 plus 80 is 200. So I lose, these should technically all be negative, by the way. Now I lose 200 volts, and that's equivalent to my battery voltage, which is 200 volts. Okay, take a moment and see if you can't make this clear in your mind. Okay, let's take this outer one here. So minus 60 minus 20 is minus 80, minus 20 is minus 100, minus 20 is minus 120, minus 80 is 200. Okay. Let's look at one where it's a little bit different. So so let's follow this loop around here. Okay, minus 20 because I'm going with the current. Minus 20 was minus 40. Minus 20, which means I'm going with the current. So right now I'm at minus 60. Now I'm going to go upstream to get to this point where I started, and I'm going to go plus 60, and then that adds up to 0. Okay. So there's 3 different approaches to solving this. I'm only really going to look at 2 and 3. I recommend method 3. I'm gonna basically skip over 1. Step 2 is if you're an algebra person, if you just like the math, you might do it that way. But step 3 is probably the easiest, and this is the way that I recommend. So let's look at step 2. Okay. So basically what you're going to do is we've got a circuit, and we need to set up what our unknowns are. We want to solve what we're trying to solve with the 3 currents. Okay, so I1, okay, I2, and I3. Okay. Use junction rule here. Okay. I2 equals I1 plus I3. Okay. Now we've got 3 unknowns, I1, I2, and I3, which means we need 3 equations. So right now we've got 1. Okay. That means we're gonna use the loop rule twice. Okay. So so we're gonna follow along here. We're gonna start with the battery. We're gonna follow the green. We're gonna go take the top loop, and then we're gonna come back around here. Okay. So that's gonna be minus 10 I1, minus 10 I1, minus 80 I2, because this is I2 now. Okay, plus 120 equals 0. So that's the first loop rule. And now we'll apply loop rule again. And I could have done, I didn't have to do this loop. I could have done this loop, okay, and gotten my answer. But what I did is I just solved this loop right here, okay, and that's going to be minus I2 80, okay, plus 40 I3. Okay, now it's plus because I'm going upstream on the resistor, okay, equals 0. Okay, then you just solve 3 equations simultaneously. Okay, so sub in for I1, etc. Get that equation, etc., etc., etc. If you want to analyze this, feel free to pause this and take a look at this more in depth. And we're done. Okay. This is the method that I recommend. It's kind of a hybrid of the first one that I didn't show you, and this is what you do. Okay, you find the equivalent resistance, and then find what typically is going to be called I1. Okay, so solve for the REQ. So that'd be 1 over 80 plus 1 over 40 equals 1 over REQ, which must equal 26.7, okay, plus 10. Break this down just like we did before, and find the equivalent resistance is equal to 36.7. Okay. That equivalent resistance is, if I were to convert this all into one resistor, what it would be, that's going to give me the current flowing out of my battery. That's not going to give me these currents, okay, because I've essentially collapsed them. You remember when I converted this into a single resistor? Okay, so when I do that, I lose my my resolution per se here, and I'm just, all I can look at is I1, okay, and use V equals IR, 120 volts equals I1 times 36.7, and we get that I1 is equal to 3.3 amps. Okay. hopefully you followed me with that equivalent resistance bit. All right, so that's step one. Now we know I1. Now we just have two unknowns. Okay. Now probably what we want to do is use a loop rule. Okay, and we're going to say just like we did before, 10I1 minus 80I2. Okay, plus 120 equals 0. Okay. Sub in for I1, you get I2 equals 1.1. And then all we have to do is use junction rule. Okay. And junction rule is that this 3.3 equals these two added together. So it's got to be 2.2. Okay. I went through that kind of fast because I had this all prepared on the screen. Hopefully that made sense. That's really the end of the notes for the whole year, by the way. So take some time and get a hold of this, and I will feel free to stop by during office hours or email me. Okay, bye bye.